All right, good morning, good afternoon, good evening, wherever you're at. Hope you're doing great. Thanks for joining me for the second half of section 6.2, talking about properties of parallelograms. Yesterday we talked about how the opposite sides of a parallelogram are congruent and the opposite angles of a parallelogram are congruent, okay? So those are some things to think about as we proceed forward. Now, what we're going to be talking about today, Theorem 6.3. So on a blank sheet of paper or at the top of your notes there, you got a little bit of space. You can actually go ahead and draw in the proof for Theorem 6.3, which is going to be this. I'm going to go ahead and jot down a parallelogram here. And what we're going to look at are the diagonals of the parallelogram, because they do something to each other, okay? And so what I want you to do is I want you to go ahead and label that point E right there. And let's just go ahead and start to list off some things that we know about, let's say these two triangles right here, AED and CEB, okay? Well, I hope you remember, like I said, the opposite sides are congruent, okay? I would look at these two triangles and probably initially put the vertical angles congruent, okay? And then from there, you know, with this line being parallel to this line, we've got some alternate interior angles here. You could either mark this angle here congruent to this angle here, or you could go with this angle here congruent to this angle here. It really doesn't matter. And so I'll just go ahead and do this right here. Okay. And so those two triangles, AED and CEB, are congruent. You could either say by angle, angle, side, or angle, side, angle. The way I've marked it up there again is by angle, angle, side. Okay. So why did we do all that? Well, we want to look at the diagonals and see what they do to each other. So BD and AC. And so if we look at those diagonals, what you see is that if these triangles are congruent, this segment here has to be congruent to this segment here by CP/CTC. And this segment here has to be congruent to this segment here, again by CP/CTC. So what did the diagonals do to each other? Well, do you see how this diagonal cut this diagonal in half because of the congruency marks here? And then do you see how this diagonal cut this diagonal in half because of the congruency marks here? Okay. What do we call that when something's being cut in half? Well, it's being bisected, right? And so for Theorem 6.3, you can go ahead and fill that in. The diagonals of a parallelogram bisect each other, okay? Now, for Theorem 6.4, I might want to get a ruler out for this one just to be a little more precise. Put this guy away. Goodbye, okay? So, if I go ahead and draw a line, drop down a little bit, draw another line, drop down a little bit, draw another line. Okay? And let's do this. I'm going to draw two more lines. I'll draw a line that's completely vertical there. Straight up. Oh, was straight up and down. Okay. Try this again. There we go. Okay. All right. So let's say for a moment that these lines are all parallel to each other. Okay. Which I think you can tell that they are. And let's set the spacing between these lines is all equal. Okay. Now, I'm going to draw another line over here. Let's say this line right here. And the question I want to ask you guys is this. Since the spacing here is all equal, does that mean that this length will be equal to this length, which will be equal to this length? And the answer is yes and no, okay? So the yes part is yes, all of these lengths here, here, and here will all be equal to each other. However, these lengths here will not be equal to this length here. I think you can see that this length here is smaller than this length here. And so I want to add another congruency mark there to finish things off, okay? And so in Theorem 6.4, it reads this, and you want to fill this in. If 3 or more parallel lines cut off congruent segments on one transversal, so that's what we're talking about here. 3 or more parallel lines are cutting off congruent segments along one transversal. So this would be the one transversal it's referring to. Then they cut off that fill-in-the-blank congruent segments on every transversal. So we're not saying that these segments will be congruent back to the original transversal segments. They're going to be congruent to each other. They cut off congruent segments with respect to each other. Okay? So let's see how this all plays out here. If we take a look back at our notes here, let me go down just a bit here. All right. In this picture right here, we're told up above that all these lines are parallel to each other, which is good. And we can see that this segment here is congruent to this one, which is congruent to this one. It's kind of the same as my picture, but in reverse. And so it's not that this segment equals this one. Okay, it doesn't. And so these segments will all equal each other. So this is 2.5 here, and this is 2.5 there. Now, if I want to find EH, be careful with this. A lot of times I have students that will count the points here, and they'll multiply 2.5 times 4, when in actuality, how many spaces are there between these? There's only 3, and so if I take 2.5 times 3, or 2.5 plus 2.5 plus 2.5, we end up with, let's see here, 7.5. So EH has a length of 7.5 there. Okay. For the next one, this one gets a little more tricky. Obviously, more lines, more things to consider, but here's the basis. All these lines are parallel to each other. You can see that by the arrows. And they're all spaced evenly. You can see that by the congruency marks cutting that transversal. Okay? And so what we're told is that AE is a length of 17. Okay? And we're also told that this shape right here is a parallelogram. Okay? So what I'm thinking right now is, okay, if this is 17, I know this is 17, this is 17, this is 17, and this is 17. So I'm going to go ahead and take 17 plus 17 to get my length of NX, which is going to be 34. Okay? Now, the reason why I include in the directions there that this is a parallelogram is because the opposite sides of a parallelogram are what? They're congruent, right? So if I look up here at B to L, that's also going to be 34 units as well. Okay? Now the next one's a little bit easier. Let's see here. BF has a length of 18. So this length here is 18. So I know that this length here is 18. And then this length here is also 18. 18 times 3 is 54. And so BN has a length of 54. Okay. Again, this is a parallelogram. So what is the length of XL? It's also 54 units long. Okay. So again, just applying that if we have parallel lines, it breaks it up evenly. Pretty simple. Okay. Now, let's go ahead and skip to the bottom of your paper here. I'm going to have you guys go ahead and do the rest of these problems on this worksheet here because I don't think it'll take you very long. But as we look at the last problem here, this one's a little bit more difficult here. All of these problems on this worksheet here deal with, the rest of these problems deal with the fact that diagonals bisect each other. Okay? In fact, before I go and do the last one, let me just bring this to your attention. This length right here is the 4x plus 3, not the whole diagonal, but just that length right there. And so IK we know is 35, so you should be able to set up an equation if the diagonals bisect each other there. Okay? So, in looking at this picture, the first thing I'm probably going to do is just go ahead and show that these diagonals bisect each other. Now, immediately I should know what the equation is going to be for both x and y. Okay? I've got one equation that will be y equals x plus 1. Okay? All right, and then the other equation is going to be, let's do 3y minus 7 is equal to 2x. Okay. Now there again are lots of different ways you can go about solving this type of problem right here, but I think the easiest way probably is to go ahead and substitute in this expression right here in for the y value over here. Okay, and so, you know, if y equals that, I've already got y by itself, I can substitute that in. So if I go ahead and do this, 3 parentheses x plus 1 minus 7 is equal to 2x. Now we can go ahead and solve for x. Okay. Now again, you guys can probably do it faster than I can up here on the board, but you know, if you want to fast forward and try to work it through quickly, that's fine with me. Obviously, I'm going to go ahead and get rid of the parentheses first. So 3x plus 3 minus 7 is equal to 2x. Okay. Might as well combine like terms. 3x minus 4 equals 2x. Okay. You can do multiple things from there. I'm probably going to subtract 3x from both sides. So that will give me negative 4 equals negative 1x. And then divide through by negative 1, you're going to get x equal to 4. Okay. So the fact that I have a positive length is a good thing. So I know what BE is. It's a length of 5. And what should y be? It should be 5 as well. So I can plug that 4 back in over here just to justify that. Y equals 4 plus 1. Y will equal 5. Okay. And so as to double check this, we've got BE and ED are both 5. If I plug the 4 in for EC, I get 8. If I plug the 5 in for AE, you get 3 times 5, 15 minus 7, that's also 8. Okay, so I know I've done it correctly. All right, so like I said, go back and finish up the rest of that worksheet for me, and then you can come back here and take a look at how you did. In the meantime, I would probably pause me because it'll just distract you probably to do the rest of the work here. But I will be back to show you how to do the rest of these if you didn't get them done right. Okay. All right, looking at this first problem here, diagonals bisect each other, right? Well, that's easy. X is 15. Okay. In the second problem, diagonals bisect each other. So I know the equation. And now I just have to go ahead and solve for x. Okay. So if I add 4, divide by 2, I get x equal to 7. Okay. Likewise in the next one, nothing's changing. Everything, you know, status quo, pretty easy. X minus 4 equals 28. Add 4. You get x equal to 32. Okay. So far, so simple. All right. Looking at the next one, again, the diagonals bisect each other, so we get the equation 4x minus 10 is equal to 3x minus 2. If I go ahead and subtract 3x from both sides, I just get x. If I add 10 to both sides, I get 8. So I know x is equal to 8. Now again, you can plug this back in. 3 times 8 is 24 minus 2, that's 22. Over here, 4 times 8 is 32 minus 10, that's also 22. Just another way of double checking yourself. Okay. In this next problem, if I go ahead and show the diagonals bisect each other, we know that AC is 24, so you could go ahead and do 2x, or x plus x equals 24, but x is going to be half as much. Okay, so x is a length of 12. Okay. Kind of the same thing, but in reverse. If EG is x, and we know that the diagonals bisect each other, we know that x will have to equal 8, or the length of EG is going to be a length of 8. Okay. So I really hope that those first 6 problems there were really simple for you. Those were not meant to be difficult problems. let's look at the next one here. I would assume some people may have struggled a little bit with this next one, and that's this. If I know that this length is the 4x plus 3, okay, and the diagonals bisect each other, that means I'm either going to do 4x plus 3 plus 4x plus 3 equals the whole length, which is 35, or I can just double it. Okay, either way, I have the correct equation there. So if I work this out, 8x plus 6 equals 35. If I subtract 6, I get 29. Ooh, that's going to be an interesting fraction there. 29 divided by 8, well, 8 times 3 is 24. And there's 5 left over, so it'll be 5/8 right there. I'm not sure what that is as a decimal, 3.6, 3.7, something like that. But that's the answer there for that one. Continuing the same process, this one might be easier for most people. Diagonals bisect. So we have 6x minus 22 equals 4x minus 4. If I go ahead and subtract 4x from both sides, and I add 22 to both sides, and then divide through by 2, I get x equal to 9. Okay. Again, might want to double check here. If I take 9 times 6, that's 54, minus 22, that would be 36. Did I do that right? 9 times 6 is 54. Oh, no, 32. Sorry. Okay, so 54 minus 22 would be 32. And then 9 times 4 is 36, minus 4 is also 32. So we know that x is correct there. X equals 9. I want to find the length of TI. If I know TR is 14 and ME is 31, okay, this right here is just there to throw you off. Okay, so if TR is 14 and the diagonals bisect each other, I know that TI has to be 28, a length of 28. So again, I hope that wasn't very difficult. You know, there's a couple curveballs I can throw at you, like this last problem, or maybe like this problem right here. Okay, but for the most part, I hope that you were able to apply what we talked about today and can have great success with that concept there. So, like usual, if you're taking notes for me, make sure you show me those notes. I'll give you credit for that, and there is homework on the web page to be done. So, thank you for your time. Have a great day, and I will see you later.